We've got something here that we haven't really talked about yet. Each of the particle groups has a bunch of parameters up at the top. Let's just take a quick look at those. We've got an elasticity. This is going to define how much kind of bounce or energy is involved in the particle. Dynamic friction for when they actually hit other particles. How much energy is going to be lost. And static friction, so if they're just at rest, how much friction are they going to have with other things. That'll keep them from sliding off floors and stuff. Let's see, and then we've got delay frames. Delay frames is interesting because once a particle is born, it's going to wait this many number of frames before adding him to the shape collision simulation. And what that'll do is it'll give them a chance to move out in space, maybe separate so they're not all clumped up in the beginning, and it will add them once they reach that point in time. Which group are we on? Yeah. And then we've got optimize. Optimize is going to enable this group of controls down here at the bottom. Definitely recommend that you read the help file, but basically what it does is it's going to allow that particle group to have its shape collision be optimized. And so it's going to analyze the shape of the particle involved and say, oh, are you under 50 faces? If you are, then we're not going to optimize you. But if you're over 50 faces, then yes, we want to have you subject to optimization. And these face thresholds and edge thresholds bias maximum edge length and preserve smooth boundaries. Those are going to kind of alter what the particle's shape looks like when it's being looked at in the collision engine. And that's going to be different than what you actually see in the viewport. It's going to have face thresholds, angles between faces, and all these other settings. So definitely read the help file on that. That's a good one. Let's just take a quick look, make sure we didn't leave anything out. Oh yeah, here we are back on shape collision. It's got an option here for the recorder, so you can actually record your shape collision to a file, and that's going to cache it out just like we do master dynamic or dynamic sets, so that you don't have to recalculate that shape collision every single time. That could save quite a bit of time in CPU. Shape collision has the same kind of optimize functions here. Those are going to be used for the floor, whether or not the floor gets optimized. Let's see. Last but not least, we've got the physics section of shape collision. This is a specific rollout to shape collision, and it's going to allow you to define how many collision iterations to calculate per sample, or how many contact iterations. We've got two different types of contact. We've got type 1 and type 2. Type 1 is more optimized, it's faster. Type 2 is extremely accurate. So if you need the absolute highest quality, use contact type 2. And then we have some controls down here at the bottom. These are actually to remove particles from the collision simulation at a certain time, or when they are performing a certain way. The way this works is this deactive time is it's a time window for which to look at the particle and say, okay, during this amount of time, is his velocity this or less? Is his rotation threshold this or less? If either of those, if the particle is not moving very fast and he's not rotating very much, then we're going to go ahead and take him out and just tell him to stop. Stop being part of the collision simulation. Basically, you are now frozen. And what happens there is that particle then obviously doesn't get calculated, but if we want other particles to be able to come back in and hit him and knock him around again, you're going to need to turn on activate all. And this is going to allow the simulation to wake up frozen particles after they've been deactivated. So the whole deactivation is so that when you get particles piling up on the floor, maybe they're bouncing, you don't want them to continue to bounce non-stop, and take out every last bit of energy. You kind of want them to come down, hit a few times, and then stop, and not continue to move. No dancing particles. And so you can lower these values to make that happen faster. So right now it's doing, I think this is 0.5. Yeah, 0.5 doesn't say if it's seconds or frames or samples, but you'll be able to definitely see the difference. If you lower this, it's basically going to only look at the particle for a smaller amount of time, and so it'll turn him off and freeze him faster. Likewise, if the velocity threshold is lower, like if we set the velocity threshold to 1, it's going to require that that particle be moving 1 or less, with a speed of 1 or less, in order to be frozen. So that's actually going to make the particle live longer. What you would want to do to make him be frozen faster is set it to something like 5 or 10, and that's going to take him out really quick. Same with rotation threshold. If you set it to 180, anyone with a rotational speed of 180 is going to go ahead and be told to be frozen. Now that's probably a little too fast, so I would probably recommend just using the default values and doing some experimenting to find out. But do remember, you want to activate all to be checked if you want those frozen deactivated particles to be woken up when some other particle comes in and collides with them. Okay, so I think that's pretty much it right now for shape collision. We took a look at the particle has the shape collision dynamics properties, optimize, active, neutron, frozen. Those are the big ones. Voxel grid for how finely his overall shape is going to be evaluated. Edge samples for specific edge division and sampling. Frozen first activation when he's frozen there. And then deformation is a great one. And then of course each particle group has its own shape collision optimize capabilities. Okay, so I think that's it for shape collision. We're going to go ahead and move on to PhysX.